Something is happening on Mars right now. Something that's making scientists around the world lose sleep. Something that could change everything we thought we knew about life in the universe. For decades, we've been searching, scanning the red desert of our neighboring planet, looking for answers to the biggest question humanity has ever asked. Are we alone? And now we might finally have our answer. But here's the thing. What we found, it shouldn't be there. Before we dive into this incredible story, I want to know, where are you watching from? Let's see how global our community is. Now, back to our story. The discovery we're about to explore is so significant that Oleg Abramov from the Planetary Science Institute calls it arguably the best evidence we have so far for microbial life on early Mars. Let that sink in. The best evidence. Not just interesting, not just curious. The absolute best proof we've discovered in over 50 years of Mars exploration. This is the story of a rock. A simple rock, sitting in an ancient river valley on Mars. But this rock has patterns on it. Spots, like the spots on a leopard's skin. And those spots are driving the scientific community absolutely crazy. Because on Earth, there are only two ways these patterns can form. One way requires extreme conditions we haven't found on Mars. The other way, life. Welcome to the most important discovery of our generation. Buckle up, because what you're about to learn will blow your mind. Before we get to the discovery itself, we need to understand Mars. Because this planet, our neighboring world, holds secrets that go back billions of years. Mars is the fourth planet from the Sun. It sits about 140 million miles away from us on average, though that distance changes as both planets orbit the Sun. It's roughly half the size of Earth, with a diameter of about 4,200 miles, compared to Earth's 7,900 miles. Today, Mars is a frozen desert. The average temperature is minus 80 degrees Fahrenheit. That's colder than Antarctica in winter. The atmosphere is incredibly thin, about 100 times thinner than Earth's atmosphere, and it's made up of 95% carbon dioxide. You couldn't breathe it even if you tried. The surface pressure on Mars is so low that if you stood on the Martian surface without a spacesuit, your blood would literally boil, not from heat, but from the lack of pressure. Water on Mars can't exist as a liquid at the surface. It either freezes solid or evaporates directly into gas. But here's the incredible thing. Mars wasn't always like this. Scientists have discovered overwhelming evidence that ancient Mars, the Mars of 3 to 4 billion years ago, was a completely different world. It had a thicker atmosphere. It was warmer, and most importantly, it had liquid water. Lots of it. How do we know this? The evidence is everywhere. Orbital satellites have photographed ancient river channels carved into the Martian surface. We've found dried-up lake beds. We've discovered minerals that only form in the presence of liquid water. We've seen evidence of massive floods that once raged across the planet. In 2015, NASA announced that they had found definitive proof of liquid water still flowing on Mars today, albeit only seasonally and in very small amounts. Dark streaks appear on Martian slopes during warm seasons, suggesting that briny water still flows occasionally. But billions of years ago, Mars might have had rivers, lakes, maybe even oceans. Some scientists believe that up to 20% of the Martian surface was covered by water. That's not as much as Earth's 71%, but it's still substantial. One proposed ocean, called Oceanus Borealis, might have covered much of Mars's northern hemisphere. It could have been about the size of Earth's Atlantic Ocean. Think about that. A world with rivers and lakes, a world with rain falling from clouds, a world where water pooled in craters and flowed downhill, carving valleys and creating deltas. It sounds like Earth, doesn't it? And that's exactly why Mars is so important in our search for life. Because on Earth, wherever we find liquid water, we find life. In the deepest oceans, in boiling hot springs, in the frozen lakes of Antarctica, under miles of rock in underground caves, life finds a way to survive anywhere water exists. So the big question is, if Mars once had abundant liquid water, did it also have life? This question has driven Mars exploration for decades. Every mission we send to Mars is designed to answer this fundamental question, and every mission brings us closer to the truth. But what happened to Mars? Why did it change from a potentially habitable world to the frozen desert we see today? The answer lies in Mars's core. You see, Earth has a strong magnetic field generated by its molten iron core. This magnetic field acts like a protective shield, deflecting harmful solar radiation and preventing our atmosphere from being stripped away by the solar wind. Mars once had a magnetic field too. We know this because ancient Martian rocks still carry magnetic signatures. But about 4 billion years ago, Mars's core cooled down. The magnetic field disappeared. Without that protective shield, the solar wind, a constant stream of charged particles from the sun, began stripping away Mars's atmosphere. Over millions of years, the atmosphere thinned. As it thinned, the surface pressure dropped. Water could no longer exist as a liquid. The planet grew colder and colder. Mars died. Slowly, gradually, over hundreds of millions of years. But here's the hope. If life emerged on Mars during those early, wetter years, it might have left traces behind. Fossils, chemical signatures, patterns in rocks, and that's exactly what we might have found. Now let's talk about the machine that made this discovery possible. The Perseverance rover. Because this isn't just any robot. It's the most sophisticated piece of technology we've ever sent to another planet. Perseverance launched from Earth on July 30th, 2020, riding atop an Atlas V rocket. It traveled for 7 months through the void of space, covering over 290 million miles. And on February 18th, 2021, it performed what NASA engineers call 7 minutes of terror. Landing on Mars is incredibly difficult. The atmosphere is thick enough to create friction and heat during entry, but too thin for parachutes alone to slow you down enough for a safe landing. Dozens of Mars missions have failed during this phase, but Perseverance made it. Using a combination of heat shields, parachutes, and a rocket-powered sky crane, it touched down gently in Jezero crater. The rover itself is massive. It's about 10 feet long, 9 feet wide, and 7 feet tall. It weighs 2,260 pounds, roughly the same as a small car. It's powered by a nuclear battery called a multi-mission radioisotope thermoelectric generator, or MMRTG. This device uses the heat from decaying plutonium to generate electricity, providing about 110 watts of power continuously. Why nuclear power instead of solar panels? Because Martian dust storms can block out the sun for weeks or even months. Solar panels would be useless, but the nuclear battery keeps going day and night for years. Perseverance is equipped with 23 cameras. Let me repeat that, 23 cameras. These include navigation cameras, hazard avoidance cameras, engineering cameras, and scientific cameras. The rover can take panoramic images, close-up microscopic photos, and even selfies. But the real scientific power comes from its suite of instruments. Let me walk you through them, because understanding these tools helps us appreciate just how significant the discovery is. First, there's Pixel, the planetary instrument for X-ray lithochemistry. This device shoots X-rays at rocks and analyzes the light that bounces back. Different elements emit different wavelengths of light when hit with X-rays, so Pixel can identify the exact chemical composition of rocks down to tiny details. Then there's Sherlock, which stands for Scanning Habitable Environments with Raman and Luminescence for Organics and Chemicals. This instrument uses ultraviolet light to detect organic molecules and minerals. It can identify compounds that might be associated with ancient life. There's also SuperCam, which can fire a laser at rocks from up to 20 feet away. The laser heats the rock surface to over 18,000 degrees Fahrenheit, vaporizing a tiny amount of material. By analyzing the light from this plasma, SuperCam can determine what the rock is made of without even touching it. MOXIE, the Mars Oxygen In Situ Resource Utilization Experiment, is testing technology to convert Mars's carbon dioxide atmosphere into oxygen. This is crucial for future human missions. And there's the Radar Imager for Mars's Subsurface Experiment, or RIMFAX, which uses ground-penetrating radar to see beneath the Martian surface, revealing underground structures and layers. But perhaps most importantly for our story, Perseverance is equipped with a drill and a sample collection system. The rover can drill into rocks, extract cylindrical cores about the size of a piece of chalk, and seal them in ultra-clean titanium tubes. These sample tubes are then stored inside the rover's belly. The plan, the hope, is that a future mission will come to Mars, collect these tubes, and bring them back to Earth for detailed analysis. This is called the Mars Sample Return Mission, and we'll talk more about it later. But for now, just know that Perseverance has been collecting the most important rock samples in human history. The rover can drive about 400 feet per day when it's moving quickly, though usually it moves much more slowly to carefully study its surroundings. It's controlled by a team of engineers and scientists at NASA's Jet Propulsion Laboratory in California. But here's the thing, controlling a rover on Mars isn't like playing a video game. Because of the distance between Earth and Mars, radio signals take between 5 and 20 minutes to travel one way, depending on where the planets are in their orbits. That means if Perseverance is about to drive off a cliff, by the time the engineers see it happening and send a stop command, it's already too late. The rover has to be semi-autonomous, making its own decisions about how to avoid hazards. Every day, the team on Earth plans out the rover's activities for the next Martian day, or SOL. They upload these commands to the rover, and then Perseverance executes them independently. The next day, it sends back data and images showing what it accomplished. It's a slow, methodical process, but it works. And that brings us to Jezero Crater, the location Perseverance is exploring. Scientists chose this spot very carefully. Jezero is a 28-mile-wide crater formed by an asteroid impact billions of years ago. But what makes it special is what came after the impact. Water filled the crater, creating a lake, and rivers flowed into this lake from the west, creating a delta where sediments and nutrients accumulated. On Earth, river deltas are incredibly rich environments, teeming with life. If life ever existed on Mars, Jezero Crater is one of the best places to find evidence of it. The ancient lake in Jezero was about the size of Lake Tahoe in California. It persisted for millions of years, giving plenty of time for life to potentially emerge and thrive. So Perseverance has been slowly, carefully, methodically exploring this ancient lake bed, driving across what was once a river delta, taking samples, analyzing rocks, searching for signs of ancient life, day after day, week after week, month after month, and then it found something. It was during a routine drive through the Delta region that Perseverance's cameras spotted something unusual. A large rock, sedimentary in nature, sitting among the Martian dust. The mission scientists, examining the images from their computers on Earth, saw something that made them pause. This rock was different. It had patterns on it, spots, pale spots, ringed with dark material. They decided to take a closer look. They gave the rock a nickname, Chayava Falls, named after a waterfall in the Grand Canyon. Perseverance approached the rock carefully. It positioned its instruments, and then it began the most detailed analysis it had ever performed on a Martian rock. What it found was extraordinary. Let me describe what Chayava Falls looks like. It's a reddish-brown sedimentary rock, probably formed from mud and silt that settled at the bottom of the ancient lake billions of years ago. But across its surface are dozens of pale, whitish spots, each about the size of a large coin. Each spot is surrounded by a ring of darker material, creating a pattern that looks remarkably like a leopard's spots. These aren't random. They're too regular, too consistent. They're clearly the result of some specific process. First, Perseverance used SuperCam to analyze the chemical composition from a distance. The rock is rich in hematite, which is iron oxide. This is significant because hematite forms in the presence of liquid water. It's essentially rust. The presence of hematite confirmed that this rock formed in water, which makes sense given that it's sitting in an ancient river delta. But then things got interesting. PIXL, the X-ray instrument, examined the rock more closely. It found that those pale spots have a different chemical composition than the surrounding red rock. The spots are enriched in certain minerals, while depleted in others. Specifically, the instruments detected vivianite, an iron phosphate mineral, and gragite, an iron sulfide mineral. Now, if you're not a geologist, those names might not mean much to you, But to scientists studying the possibility of life on Mars, these minerals are incredibly exciting. Here's why. On Earth, both vivianite and greigite are commonly associated with microbial life. Microbes, tiny single-celled organisms, can use these iron-based minerals as energy sources. They essentially eat them, using chemical reactions involving these minerals to power their cellular processes. Wherever you find these minerals on Earth, you often find microbes nearby. They're like a calling card for microbial life. But it gets even better, or more complicated, depending on how you look at it. Sherlock, the organic molecule detector, found something else in the rock: organic compounds, molecules containing carbon atoms. Now let's be very clear about what organic means in this context. In chemistry, organic molecules are simply molecules that contain carbon atoms bonded to hydrogen atoms. They don't necessarily come from living things. Organic molecules can form naturally through non-biological processes. They exist in meteorites. They form in the clouds of space. They can be created by chemical reactions between rocks and water. So finding organic molecules doesn't automatically mean life, but it's still significant because life as we know it is based on organic chemistry. Every living thing on Earth is made of organic molecules. Unfortunately, Perseverance's instruments aren't sophisticated enough to determine exactly what kind of organic molecules are present in Chiava Falls. They can detect that organics are there, but not their specific structure or composition. To answer that question, we'd need to bring the sample back to Earth and analyze it in a laboratory with much more powerful equipment. But let's take stock of what we know so far. A rock formed in ancient water with a distinctive spotted patterns, containing minerals associated with microbial life on Earth. With organic molecules present, each piece of evidence by itself could be explained away, but together they paint a very intriguing picture. Now let's talk about those leopard spots in more detail, because this is where things get really interesting. On Earth, geologists have observed these same kinds of patterns in rocks. They're not common, but they're not unknown either, and scientists have studied how they form. There are, as I mentioned earlier, two main ways these leopard spot patterns can form on Earth. The first way involves high temperatures and acidic conditions. When iron-rich rocks are exposed to temperatures of several hundred degrees Celsius and are bathed in acidic fluids, chemical reactions can create these spotted patterns. The iron minerals in the rock undergo changes, creating areas of different composition that appear as spots. This process is well understood. We've observed it in volcanic areas and in industrial settings where hot, acidic conditions exist. So the scientists looked at the geological context around Chiava Falls. They examined the surrounding rocks. They looked for signs of volcanic activity or acidic conditions in the ancient past, and they found nothing. No evidence of the high temperatures needed, no signs of acidic conditions. The delta where Chiava Falls was found appears to have been a relatively calm, neutral environment, more like a modern river delta than a volcanic hellscape. So if the first explanation doesn't work, that leaves the second explanation. The second way these leopard spots form on Earth is through biological activity, specifically through the action of microbes. Here's how it works. Microbes living in rocks or sediments consume certain minerals for energy. As they metabolize these minerals, they change the chemistry of the rock around them. Some areas become enriched in certain elements, while other areas become depleted. Over time, these chemical changes become visible as patterns in the rock. The microbes essentially paint the rock through their metabolic processes. Scientists have observed this happening in modern environments, in wetlands, in lake sediments, in caves. Wherever microbes are active in rocks, they leave behind chemical signatures that can persist for millions or even billions of years. The patterns in Chiava Falls look remarkably similar to these biologically created patterns on Earth. But here's the problem. Similarity doesn't prove causation. Just because two things look alike doesn't mean they form the same way. This is where the scientific method becomes crucial. Scientists can't just look at something and say, "That looks like life, therefore it's life." They have to consider every possible explanation. They have to rule out all the non-biological explanations before they can even begin to claim they've found evidence of life. Oleg Abromov, the scientist from the Planetary Science Institute we heard from earlier, puts it this way. It's intriguing and definitely worth further study. That might sound like a cautious, underwhelming statement, but in scientific terms, intriguing and worth further study is about as excited as scientists get without definitive proof. He also said, remember that this is arguably the best evidence we have so far for microbial life on early Mars. So let's be clear about what we're saying and what we're not saying. We are not saying we've found definitive proof of life on Mars. We are not saying that we're certain Chayava Falls was created by microbes. What we are saying is that we've found a rock on Mars with multiple lines of evidence that on Earth would strongly suggest biological activity. We're saying that this evidence is stronger, more compelling, and more difficult to explain through non-biological processes than anything we've found before. We're saying that if someone showed you this rock and told you it came from Earth, you'd probably think it was created by microbes, but it didn't come from Earth, it came from Mars, and that changes everything. Now, you might be wondering, if this evidence is so compelling, why aren't scientists jumping up and down with excitement? Why aren't there press conferences with the president? Why is everyone being so careful with their language? The answer lies in a story from 28 years ago, a story about another rock from Mars, a story that taught the scientific community some hard lessons about extraordinary claims. Let's go back to August 7th, Washington, D.C., NASA headquarters, a room full of reporters, cameras, and microphones. Standing at the podium is David McKay, a respected NASA scientist. Next to him are his colleagues, looking nervous but excited. They're about to make an announcement that will make headlines around the world. They have a meteorite, a rock that fell from space and landed in Antarctica in 1984. It was found in the Allen Hills region and was labeled ALH-84F01. Scientists had determined that this meteorite came from Mars. About 16 million years ago, an asteroid slammed into Mars with such tremendous force that it ejected rocks from the Martian surface into space. Some of those rocks eventually fell to Earth as meteorites. ALH-84F01 is one of them, and it's old, very old, about 4 billion years old, making it one of the oldest known Martian rocks. But what McKay and his team found inside this ancient rock was stunning. First, they found organic molecules called polycyclic aromatic hydrocarbons, or PAHs. These are complex organic compounds. Second, they found tiny globules of carbonate minerals. These minerals can form in water and are sometimes associated with biological processes. Third, they found microscopic crystals of magnetite and iron sulfide arranged in specific patterns that on Earth are typically created by bacteria. And fourth, most dramatically, they found tiny worm-like structures in the rock, structures that looked like fossilized bacteria. They were incredibly small, about 20 to 100 nanometers in length. For comparison, a human hair is about 100,000 nanometers wide. The images were striking. Under powerful electron microscopes, these structures looked like segmented worms or sausage links. They looked biological. McKay's team believed they had found evidence not just of life on Mars, but of fossilized Martian microbes, actual dead bacteria preserved in rock for billions of years. The announcement was carefully worded. The scientists were clear that this wasn't definitive proof, but rather a collection of evidence that, taken together, suggested the possibility of ancient Martian life. But nuance doesn't survive the news cycle. Headlines screamed, "Life on Mars." The story was everywhere. Every news channel, every newspaper, every magazine. President Bill Clinton himself gave a speech about the discovery, saying, "Today, Rock 84F01 speaks to us across all those billions of years and millions of miles. It speaks of the possibility of life. If this discovery is confirmed, it will surely be one of the most stunning insights into our universe that science has ever uncovered." The world went crazy. People were thrilled, excited, some were scared. The idea that we weren't alone in the universe, that life had emerged independently on another planet, was overwhelming. scientists around the world immediately began studying ALH 84401. They wanted to verify the findings, they wanted to understand what they were seeing, and slowly, carefully, methodically, they began to poke holes in the theory. The PAH organic molecules. Other scientists pointed out that PAHs are common in space. They form naturally without life. They're found in meteorites that definitely don't contain life. And ALH 84401 had been sitting in Antarctica for 13,000 years. It could easily have been contaminated by Earth-based organic compounds. The carbonate minerals, yes, they can form in water, but they can also form through high-temperature processes that have nothing to do with life. The magnetite and iron sulfide crystals. While bacteria do create these patterns on Earth, inorganic processes can create similar patterns too, and those tiny microfossils. This is where things got really problematic. Scientists pointed out that these structures were far too small to be cells as we know them. Even the simplest bacteria on Earth are about 200 to 1,000 nanometers in size. They need to be that big to contain all the molecular machinery required for life: DNA, ribosomes, proteins, membranes. The structures in ALH 84001 were only 20 to 100 nanometers. They were too small to contain the necessary components of life. Other scientists demonstrated that mineral formations, purely inorganic processes, could create similar-looking structures. They looked biological under a microscope, but they weren't. One by one, each piece of evidence was challenged. Alternative, non-biological explanations were proposed. And these alternative explanations were simpler, more likely, and didn't require the extraordinary claim of extraterrestrial life. There's a principle in science called Occam's razor. It states that when you have multiple explanations for something, the simplest explanation is usually correct, and contamination plus inorganic processes is a much simpler explanation than ancient Martian bacteria. By the late 1990s and early 2000s, the consensus in the scientific community had shifted. Most scientists no longer believed that ALH 84401 contained evidence of Martian life. The excitement died down. The headlines faded. The meteorite was relegated to a cautionary tale. But here's the important thing. The scientists who originally studied ALH 84401 weren't frauds or fools. They were respected researchers who made their claims in good faith based on the evidence they had. The problem was that extraordinary claims require extraordinary evidence. And the evidence from ALH 84401, while intriguing, wasn't extraordinary enough. Moreover, there was the problem of how the discovery was announced. The press conference, the presidential speech, the media frenzy, all of this created unrealistic expectations and put enormous pressure on the scientific community. Which brings us back to Chayava Falls. Because the scientists studying this new potential biosignature are acutely aware of the ALH 84401 story, they're being extremely careful. They're using measured language. They're not calling press conferences with the president. But here's what's important. Even with all that caution, they're still excited. Abramov says this new finding is arguably the best evidence we have so far for microbial life on early Mars. Think about that. They know the history, they know the pitfalls, they know how easy it is to be wrong about these things, and yet they still think this is the best evidence we've ever found. Why? What makes Chayava Falls different from ALH 84401? Several things. First, we found Chayava Falls in its original context. It's sitting in an ancient river delta on Mars, exactly where you'd expect to find evidence of ancient life if it existed. We're not dealing with a meteorite that's been blasted into space, irradiated by cosmic rays, and then contaminated on Earth. Second, we have multiple independent lines of evidence, all pointing in the same direction. The leopard spots, the minerals associated with microbial life, the organic compounds, each piece supports the others. Third, we've ruled out some of the non-biological explanations. There's no evidence of the high temperatures or acidic conditions that could create these patterns through purely chemical means. And fourth, we have the sample, Perseverance drilled into Chava Falls and extracted a core sample. That sample is sitting in a sealed tube, waiting. If we can get it back to Earth, we can analyze it with instruments far more powerful than anything on Perseverance. So let me bring all of this together and talk about what needs to happen next. We have found the best evidence yet for ancient life on Mars. A rock with patterns, minerals, and organic compounds that on Earth would strongly suggest biological activity. The evidence isn't definitive, it's not proof, but it's compelling, it's exciting, it's exactly the kind of discovery that should push us forward to investigate further. Oleg Abramov from the Planetary Science Institute said it best. In terms of a definitive answer, the way I look at it is, as scientists, we get closer and closer to the truth without quite getting there. So in terms of saying definitively whether it is life or not, that is going to be very difficult, if not impossible. And maybe that's okay. Maybe we'll never have 100% certainty. Maybe there will always be some room for doubt, some alternative explanation that we can't completely rule out. But that doesn't mean we should stop searching. It doesn't mean the evidence doesn't matter. Science doesn't deal in absolute certainties. It deals in probabilities, in weight of evidence, in building stronger and stronger cases. And right now, the case for ancient Martian life is stronger than it's ever been. The leopard spots on Chava Falls are unusual and difficult to explain without biology. The minerals present, vivianite and greigite, are exactly the kinds of minerals that microbes use for energy on Earth. The organic compounds, while not necessarily biological, are consistent with the preservation of ancient organic matter. The context, an ancient river delta where life could have thrived, makes sense. Each piece of evidence by itself is intriguing, but not conclusive. But together, they paint a picture, they tell a story. And that story is compelling enough that we need to investigate further. We need to bring the samples home. The Mars sample return mission is expensive, it's technically challenging, it faces political and budgetary obstacles, but it's also one of the most important scientific endeavors we could possibly undertake. Think about what we spend money on as a society. We spend billions on entertainment, on sports, on military hardware, on countless things that, while important, won't fundamentally change our understanding of our place in the universe. The entire Mars sample return mission, even at its most expensive estimates, costs less than what the world spends on video games in a single year. Is answering the question, are we alone in the universe worth the investment? I think most people would say yes. This is one of the deepest, most profound questions humanity has ever asked. And we're closer to answering it than we've ever been. We just need the will to follow through. There will be challenges, technical problems will emerge, costs might increase, there will be setbacks and failures. That's the nature of ambitious exploration. When President Kennedy committed America to landing on the moon in 1961, nobody knew if it was actually possible. The technology didn't exist yet. Many people thought it was a fool's errand. But we did it. We built the technology. We solved the problems. We landed on the moon not once but 6 times. We can do this too. We can bring Mars samples back to Earth. We can analyze them. We can find out if life once existed on another planet. And beyond Mars, we can continue the search. We can send missions to Europa and Enceladus to study their underground oceans. We can send humans to Mars to conduct even more sophisticated investigations. The search for life beyond Earth is a multi-generational effort. It won't be solved by a single mission or a single discovery, but each step forward brings us closer. I want to share something that Oleg Abramov said that really struck me. Getting those samples to Earth and analyzing them in proper labs is going to be our best chance of understanding what's happening. Our best chance. Not our only chance, but our best chance. If we abandon Mars sample return, we might still learn more about Mars through future missions. We might eventually send humans who can conduct investigations that robots can't. But that's decades away, maybe generations away. The samples are sitting there right now, waiting. The technology to bring them home exists or is very close to existing. This is our best chance, our best opportunity to answer the question in our lifetimes. So what can we do? What can everyday people do to help make this happen? First, Stay informed. Pay attention to NASA's budget discussions. Understand what's at stake. Second, contact your representatives in Congress. Let them know that you support space exploration, that you think the search for life beyond Earth is important, that you want Mars sample return to happen. Politicians respond to constituent pressure. If enough people make their voices heard, it matters. Third, support science education and public outreach. The more people understand and appreciate science, the more support there will be for missions like this. And fourth, stay curious. Keep asking questions. Keep learning. Share your excitement about these discoveries with friends and family. We are living in an extraordinary time, a time when the biggest questions about our existence might finally be answered. Are we alone in the universe? How did life begin? What is our place in the cosmos? These questions have haunted humanity for millennia, and now we have the tools to answer them. A spotted rock on Mars might hold the key. Or it might tell us something else entirely. Maybe those spots were formed by chemistry we don't fully understand. Maybe there's an explanation we haven't thought of yet. Either way, we learn something. Either way, we move closer to the truth. But only if we bring those samples home. Only if we have the courage and the determination to see this through. Only if we decide that answering the biggest questions is worth the effort. I believe we will. I believe that humanity, despite all our problems and conflicts and short-sighted thinking, is capable of coming together to do great things. We've done it before. We've sent spacecraft to every planet in our solar system. We've built the International Space Station. We've landed on the Moon and sent rovers to Mars. We can do this too. And when those samples come home, when scientists in laboratories around the world start analyzing them, when we finally get an answer to whether life existed on Mars, that will be a moment that defines our generation. That spotted rock on Mars is waiting for us. The question is, are we ready for the answer? This has been the story of Chayava Falls, the story of our search for life beyond Earth, the story of humanity reaching out to the cosmos, asking the oldest question, and finally, maybe, getting an answer. Thank you for watching. Now go out there and look up at the stars. And remember, we're not just staring into the void. We're searching for our place in the universe. And we're closer than we've ever been to finding it.